we'll discuss about the most common approximation done to the nonlinear estimation problem. As we indicated, there is very limited feasibility of the implementation of the optimal filter, which really requires a functional recursion. In view of this, suboptimal algorithms are of interest. There is a recursive calculation which has been developed very recently called the particle filter, which does actually what's called the Monte Carlo integration on the base formula, that integral, and stores the PDF as a sum of delta functions. This is really a subject of a separate semester-length topic, so we are not going to discuss it, but you just want to be aware that there are techniques for nonlinear estimation. They are suboptimal, but they, with enough computational power, they can be implemented. So what we'll discuss is something that is similar to the linear Gaussian case as an approximation to the nonlinear non-Gaussian case. The recursive calculation of the sufficient statistic, which consists of the conditional mean and variance or covariance matrix, in the linear Gaussian case is just about the simplest possible state estimation filter. As indicated earlier, in a linear system with non-Gaussian random variable, the same simple recursion yields an approximate mean and variance, and the example from the previous subsection indicated that is not very far from what the optimal could do. So, in principle, we are interested in a framework similar to the one-form linear system. This is our desideratum, that it would apply for a non-linear system. Such an estimator is called the extended Kalman filter, can be obtained by a series expansion of the nonlinear dynamics and of the measurement equations. The first order extended Kalman filter is based on a linearization of first order series expansion of the nonlinearities which are in the dynamic and or measurement equations. And then we do a linear minimum mean square error estimation with the approximate moments we get following this expansion. There is a second order EKF that relies on a second order expansion and includes some extra second order correction terms, and we'll see that as a byproduct of our derivation. The modeling assumptions will be x at time k plus 1 is a nonlinear function of k and xk plus vk. So unlike at the very beginning where we had that boldface f, we indicated already that we'll handle a nonlinear dynamic equation, but still the noise will enter additively. The reason for this is that with a zero mean white process noise, you can calculate a predicted state by ending up with the expected value of the noise being zero. Therefore, we only have to handle the nonlinearities related to the state. We assume there is no input, no control, and the standard assumptions on the noise mean zero, white covariance qk, might be time varying, so might be non-stationary sequence. The measurement is h of k and xk plus wk. Again, the same thing. We assume there is a measurement that is non-linear in the state, but there is linearly additive measurement noise similar to the process noise in the dynamic. So you have either f or h, at least one of them have to be non-linear now. And the measurement noise statistical properties are again mean zero, white with covariance rk, and the two sequences are uncorrelated and also uncorrelated or independent from the initial state. The initial state is modeled via an estimate x hat 0, 0, which is an approximate conditional mean and the covariance p0, 0, and it will be assumed to be uncorrelated with the two noise sequences. Similarly to the linear case, it will be assumed that we have the estimate at time k, x hat kk, which now is an approximate conditional mean, and we indicate this by using this approximate equality sign. So this is approximately the expected value of xk given zk and an associated covariance matrix or mean square error matrix to be a little bit more rigorous with the language. Now, what we have under the assumption that this estimate is an approximate conditional mean is that the estimation error is approximately zero mean. Another assumption that will be made, and this becomes important if the expansion is carried up to second order terms, then at some point we will need third order moments when you calculate, like the square of an expansion with first and second order terms takes you up to fourth order terms after the squaring, so we need third and fourth order moments. We'll assume the third order moment of the estimation error as approximately zero, so we implicitly make a quasi-Gaussian assumption still, even though things are nonlinear and non-Gaussian, and when we need a fourth moment, we'll rely again on the results from Gaussian random variables. Otherwise, the results just cannot be obtained. So, the derivation of the EKF has, the first step is how to obtain the predicted state x hat k plus 1k from our nonlinear function f of k and xk. We expand it in a Taylor series around the latest estimate x hat kk with terms up to first or second order to yield the first or second order EKF respectively. We really go up to second order, and then the first order filter follows as a particular case. What we have is a vector Taylor series expansion, namely xk plus 1, which is the nonlinear function of x, is expanded. Zeroth order term evaluated at x hat kk, so that's f of k at x hat kk. First order term, f sub x, that would be the gradient of the vector function f with respect to the vector x, that's really the Jacobian. And this is a matrix, Jacobian matrix, multiplies the difference between xk, the point at which we want the function, but we evaluate it around x hat kk, so that's the first order term, first derivative, then will be a second derivative, which is really the Hessian, and it has to be written in a slightly more complicated fashion. Hessian is a second derivative. For each component of the vector f, we need its Hessian, and then we put it in location I of an nx dimensional vector denoted as EI. This is the unit nx dimensional vector with 1 in location I and 0. So that's the basis vector for our nx dimensional space, and we sum over all I from 1 to nx, and you see the half here typical for second order terms in a Taylor expansion, plus the high order terms, plus the process noise. High order terms will be neglected, and in most cases even the second order term can be neglected. So EI is the ith nx dimensional Cartesian basis vector with the ith component unity, the remaining ones are all 0. Fx is the Jacobian of the vector, that's a matrix. F sub x is del x f transpose, the whole thing transpose, or in this very symbolic notation is the partial of the vector f with respect to the vector x. And it will have to be evaluated at some point, and we choose the best we have prior to time k plus 1, the estimate at times k, that's x hat kk. So we evaluate this at x hat kk. The Hessian is the second derivative matrix of the ith component of the vector f, so it's a del x transpose. So this is the partial of f super I ith component. And then we higher order terms which we'll stay away from. Now, given the data zk, both the Jacobian and the Hessian are deterministic because they have been evaluated at an estimate always. So the random variables are xk and vk. In the previous expansion, this is random, and these are random, and this is random. Deterministic, 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 negligible, and that's obviously deterministic. So these are the random variables of the problem. These properties will be important when taking conditional expectations next, and we are going to use the property that the state estimation errors mean is approximate is 0. Take expected value. The first order term falls out because of the 0 mean. We have the 0th order term, and based on the result from chapter 1.4.5, equation 1, we have this expression for the second order term. This is the expected value of a quadratic term. It's just the trace of the matrix in the quadratic form times the covariance of the vector which enters into that quadratic form. So here is the predicted state is the 0th term plus a second order term. If we don't go to the second order EKF, we use only this, which means we treat the nonlinearity in this case by just substituting into it x hat kk for xk, and that's it. In the linear case, the expected value of fx is really fx hat kk. In the nonlinear case, we approximate it pretty much in a similar fashion, possibly with a second order correction term. Now, what is the state prediction error if we subtract the true state from this, or subtract x minus x hat k plus 1k to give x tilde k plus 1k? The 0th order terms cancel. They are the same in the expansion and in the predicted value. We end up with the first order term, and is a second order term, plus the process noise. So we drop the high order terms, and you can see that this fx is the same as the transit. Place the role in the error equation, same role as the transition matrix was playing in the linear case. If we multiply the above with its transpose and take the expectation conditioned on z super k, we'll end up with a state prediction covariance, or really mean square error matrix. Pk plus 1k is fxk, the Jacobian, pkk times the transpose of the Jacobian, plus a term, which this is really a fourth order term. You can see Hessian, Hessian, covariance, covariance, plus the process noise covariance. So if you look at the equation in the Kalman filter, that was f transpose plus q, you see again, as already indicated in the previous equation, that what we have is the Jacobian plays the role of the transition matrix. There's another assumption, because when you multiply first order and second order term, you end up also with the third order term. That has been assumed to be 0 because we assumed, as indicated, that the third order moments are 0, and when this fourth order moment is calculated, the assumption is that this is like in the Gaussian case, namely for a scalar that's easy to remember, the fourth order moment is 3 times sigma to the fourth, where sigma square is the variance. So, And again, the first order version of this equation is the same as in the linear case, with the Jacobian playing the role of the transition matrix. Measurement prediction. Very similar to the state. We expand the nonlinear function h of x in series, zero first and second order term. In the value of the predicted measurement, all we get is the zeroth order term and the second order term. The first order, again, with the zero mean assumption, falls out. So you can see that the predicted measurement is the nonlinear function instead of x, but we'll take an x hat, k plus 1k. That's the best guess we have at time k for what the state will be next time. And again, there is a second order correction term in this case that again, in most situations it can be neglected. Now, the measurement prediction covariance, which is the same as the innovation or residual covariance, really an MSE matrix, will be S, same notation as the linear case, the Jacobian of H times the state one-step prediction covariance times the transpose of the Jacobian, plus a fourth order term that results from the second order term in the expansion, which has this mean and this covariance, plus the measurement noise covariance. So the HPH prime plus R is here, and this is the same if we limit it to first order as in the linear Kalman filter. So we have the Jacobian H sub x, that's del x H transpose, again has to be evaluated at the best guess, best value we have for x at time k plus 1, that's x hat k plus 1k, and there is a Hessian for each component of H, there is a Hessian. Now, if we limit it to first order terms, we have this remarkable resemblance, and this was the goal. The simplicity is about the same as for the Kalman filter, but there is one exception. You will need Jacobians, and the Jacobians need a state estimate or a predicted value to be evaluated as. And this brings in the risk of, if you don't have a good state estimate, you get a wrong Jacobian, which calculates your own covariance, which propagates into a worse estimate. So there is a possibility in this nonlinear filtering problem that using linearization techniques, you can drift away and end up in what could be divergence. Namely, the error grows and grows and the filter cannot correct it. This is as far as the filter equations are concerned. The remaining steps in the filter, which require us to calculate the filter gain, the update equation for the state, which is the linear combination between the predicted state and the innovation, with the latter weighted by the filter gain, are identical to those from the filter. So the state update is exactly the same thing, same equation as in the linear case. The covariance update, again, is exactly the same. At this point, it's worth taking a bird's eye view and see the flow chart of the extended Kalman filter, the first order version. So what we have is the same four columns. We have the evolution of the state, which starts at time tk is xk. It undergoes a transition, but this is a nonlinear operation on x. Vk is the process noise shown here as additive. From this new state at x, new state xk plus 1, we get the new measurement zk plus 1, again a nonlinear function of xk plus 1, and we model as an additive noise this disturbance. Known input, same thing, goes into the truth, and we know it for the state prediction. So the part that requires to estimate the state, has the first step, predict the state from k. You have an x at k at tk, to time tk plus 1, x at k plus 1k, and this is the first order filter. Just use the nonlinear equation and plug into it the latest estimate from the previous time. Measurement prediction, again first order EKF is the same thing. Use the predicted state in the nonlinear equation for the measurement h of xk plus 1. Use an x hat k plus 1k instead of xk plus 1. Residual calculation is identical, just zk plus 1 minus the predicted z hat k plus 1k. Update of the state estimate is again identical. X hat k plus 1 k plus 1 is x hat k plus 1 k plus wk plus 1 new k plus 1, where this gain will be calculated from the last column, which is the state covariance and gain computation sequence. We have the state covariance at tk, that's pkk. Now, before we can do anything to propagate the state covariance, we need the Jacobians. We don't have fixed transition matrices, we have the Jacobians. And if you go back and think of this system as linear, assume that little f of k is a cap fx. The gradient, the Jacobian of cap fx with respect to x is just the cap f. So instead of a constant, we have a partial derivative which is not a constant because now it's a nonlinear little f here. So we evaluate it at x equal to x hat kk here. Similarly, the Jacobian of the h function is evaluated at the predicted state now, that's an x hat k plus 1 given k. So these two blocks require a flow of data from the state estimation itself. They cannot be done independently of the data. And again, this is a characteristic of nonlinear estimation. The results in terms of accuracy, covariance, or mean square error will be data dependent. Once these Jacobians have been obtained, the state prediction covariance equation for the first order EKF is exactly the same, but now instead of fk being a simple constant transition matrix, it's a Jacobian of the little f. The residual or innovation covariance S will be this R plus HP prediction H transpose. The filter gain has the same expression. W is pk plus 1k, hk plus 1 transpose, sk plus 1 inverse. And the state covariance update will be again exactly the same equation as before, even though the calculation of these covariances is somewhat different due to the use of these Jacobians. So, to come back to these comments, this is the main difference. We need evaluation of Jacobians. We lost the decoupling. We cannot do it in general offline. The linearization or evaluation of Jacobians, these are the derivatives in the Taylor expansion, can be done at the latest estimate for f and at the predicted state for h. There is, however, an alternative. It can be done along a nominal trajectory, a deterministic pre-computed trajectory based on a certain scenario. This will allow offline computation of the gain and the covariance sequence. So we've got to assume that this will be the sequence of states the system will propagate along, and this allows us the offline computation. As mentioned briefly a moment ago, the stability of the EKF is not guaranteed. The conditions that we have for the Kalman filter are when you have transition matrix and measurement matrix. Now we have some approximations, and these approximations replace the transition matrix and the measurement matrix by Jacobians of the transition function and the measurement function. In the worst case, they can be the cause of divergence of the filter, namely unbounded estimation errors. So, what we showed as stability is not going to hold because our equations are not exact. Another cautionary note about the EKF. The use of the series expansion in the state prediction and or in the measurement prediction also has the potential of introducing unmodeled errors that will violate some basic assumptions about the prediction errors. What are the assumptions implicit in the EKF? That the prediction errors are zero mean. We have an unbiased prediction. That these prediction errors have covariances equal to the ones computed by the algorithm. These are crucial, and in general, if we have a nonlinear transformation, it will introduce a bias. And the covariance calculation based on a series expansion is not necessarily accurate. Therefore, there is no guarantee of stability. Furthermore, there is no guarantee that if we use second-order terms, they can compensate for such errors. All these expansions rely on Jacobians and Hessians, and the fact that we evaluate them at the estimated or predicted state rather than the exact state because we don't have them can cause errors. So, caution is definitely required in this case. Therefore, an EKF has to undergo consistency testing. The tests are exactly the same as those discussed for the Kalman filter, and only if the bias is negligible with respect to the filter calculated error variances and the mean square errors, what comes out of the covariance equations, effectively the Riccati equation for the EKF, are consistent with these variances, then we have consistency and the results can be trusted. So simulation is absolutely necessary in this case. In practice, having said all this, if the initial error and the noises are not too large, the EKF performs well. Most systems do rely on such filters, and if properly designed, they operate well and the results can be trusted. The actual limits of successful use of linearization techniques that the EKF carries out can be obtained only via extensive Monte Carlo simulations for consistency verification, which means a lot of simulations, check the consistency over many scenarios, many realizations of the noises. The results, if they are consistent, then they can be trusted.